So far, we've introduced type parameters to methods, okay, to construct generic, so-called generic method. The next step is going to be for us to look at techniques that allow us to set some boundaries on the type parameters that we accept for methods. So that brings us to the topic of bounded type parameters. So first question, what is a bounded type parameter? So it's a syntax that allows you to restrict the types that may be used as type argument for any given parameterized type. So for example, you have a generic method. This generic method takes a parameterized type t, okay? So a type parameter t, sorry. And you want to make sure that instead of just saying I accept any type parameter t, you want to say something in the lines of, well, I accept only type parameters t that are of integer-like types. So we are going to use the concept of subtyping here, okay, the concept of inheritance to specify that kind of stuff. Let's take a look at the syntax and a concrete example. So we are going back to our box of t class, right? So private field lowercase t of class t, so that's a type parameter of our class. So right now this has nothing to do with generic method, okay? We haven't introduced yet our generic method. We have a setter and a getter, just as in our previous example involving the class box of t. And now we are introducing in the lowest part of the slide, we are introducing our generic method. So it's a public void inspect method. Don't let the name fool you. It's not doing anything really semantically relevant to the concept of box. It's just going to allow us to display some information about the data type of our field t, lowercase t. Okay, you can see here that in the method inspect, we call t.getClass, then getName. So we are trying to display the name of the class of the object referenced to by field t. And then we do the same thing with a parameter of our method u. Okay, u.getClass, getName. The data type of the parameter of our inspect method is uppercase u, which is a type parameter, which is defined here. However, you can see in the highlighted yellow part that we didn't simply say we want a public u void inspect method, okay? We didn't use the u type parameter as we did in all of our previous example of generic method. We have some extraneous syntax here, extends number. So we specify that we want that type parameter to not just be anything under the sun, but a data type that extends actually the class number. For example, integer would do, double would do. So this is how we specify that extra constraint, okay? And please note that we use the keyword extend here, and it's really close to the idea of inheritance, but really it's the idea of subtyping here that is important, okay? And that will play a role, actually, this little remark, in some very specific nifty, little examples where it's obvious that we are not just using extend as a mean of trying to inherit something, define a class that inherits another class. No, we're not defining class, we're not defining interfaces here, we're not defining enums, we are actually specifying parameterized data types, right? We are trying to specify what u, the type parameter for this generic method, needs to be. So it's more of a subtyping relationship. A subtle difference, but it will make sense later on, I guess. So now that we have this extra syntax and we have this ability to specify another level of restriction on the type parameters that we are going to use for a method, let's look at what it allows us to do in practice, okay? So I have a main method on this slide, and in this main method, I have a box of integer reference variable, appropriately named integer box, to which I assign the reference of a newly created object of class box of integer. Then we use a setter, and we say, okay, this box of integer is going to contain a reference to a new integer object corresponding to the value 10. So we're just using our box of integer as it's meant to be used. Then we call the inspect method. And there is actually a problem here. We pass as our parameter lowercase u a string object, some text, a literal string object, some text. And if you remember, let's go back just one quick second to the previous slide. If you remember here, regardless of what our box generic class is supposed to hold, which was specified by the type parameter t, we have another type parameter u for the method inspect that dictates what kind of parameters we are supposed to accept. And the rule that we set was u has to extend number. When we look at this example, obviously, some text, which is a string, does not extend number. So this is going to lead to this compilation error. And the compiler is trying to tell you that the type parameter u inspect of u method in box class, okay, box of integer, actually, box of java.lang.integer class, cannot be applied when your argument is actually a java.lang.string, okay? So that's it, and that's good. I mean, actually, this is, of course, we cannot compile this, but this makes sense, right? This is why we want generics, so that the Java compiler can tell us when we are using them the wrong way. And here, the way that we are calling this method doesn't match, actually, the way the method was intended to be called based on its previous definition. Another bonus of using those bounded type parameter is that they allow you also to invoke methods that are defined in the bound. So what do we mean by that? Let's take another example. We have a public class natural number. Here is a type parameter t, which is specified, is bounded to extend integer, okay? So that means that when we create object of the class natural number, we expect that we are going to specify the parameters type t so that it actually is a subclass of integer. That's what we mean here, okay? This natural number class has a private field n, which is going to hold an object of data type t, okay? We have a constructor that works just as you would expect, and as a method, a Boolean returning method named isEven that takes no parameter and is just going to tell us if n, the field that is stored actually in the object of this class, is actually even or not. To this end, well, we call the int value method on n, and then we compute modulo 2, and if it's 0, if the remainder of the division by 2 is 0, then it is actually an even number. So we can return just the value of this expression. It's a Boolean expression, and it's going to be true or false depending on whether n is even or not. Now, the interesting bit, of course, is this call to int value. Why are we able to call n.intValue? If we wrote simply class natural number of t here, without the extend integer bit, then that generic class would not allow us to invoke int value, simply because t could be anything, and therefore the compiler would not be able to check that, you know, we can actually call this method on n because n is of the right data type. In this case, it's allowed because we said that t is not just anything. It's not just any data type, okay? T is a data type that extends integer. Any data type, any class that extends integer is going to feature the method that are provided in the class integer. Therefore, we can invoke on n any method that is defined on the bound of our parameter data type t, okay? So the bound is integer, so we are going to get an integer or something that subclasses it. Therefore, the int value method defined in integer will always be available, okay? So that's another advantage, that's another feature of actually using those bounded type parameters. They allow you to not only restrict what kind of type parameter will be specified, but they allow you also in your code to rely on this information. You know that t will be a subclass of integer, therefore you know that you can have access to a bunch of methods defined in integer and its superclasses. So What about if we are trying to introduce multiple bounds now in our example? So this is allowed. That's the first thing. That's the good news. The only thing you have to be careful about is whether you are mixing in B1, B2, and B3 here, classes and interfaces. So let's expand a little bit on that. So we have here T extends, and then we have B1 and B2 and B3. Okay, so the ampersand operator is used instead of a comma to separate all of the different data type that T is supposed to subtype. Okay, this one, the first one in the list, is of particular relevance. It's called the leftmost bounded type. Okay, and if you have to have a class among B1, B2, and B3, then it has to be specified first. Okay, that's the rule. If you try to do otherwise, you're going to get a compilation error. So if you write T extends B1 and B2 and B3, then your type variable T is considered to be a subtype of all the types listed in the bounds. Okay, so that's why you should have only one class, and then you have the extra constraint of having to specify it first. But you could say T extends the class B1. So everything can extend one class at most, and it also implements the interface B2 and B3. That's how it's meant to be used. So let's take an example illustrating this. We have a class A, an interface B, an interface C. So the code is really irrelevant. Okay, it doesn't matter. What matters is that if you define a class D, which is a generic class, and you specify that T extend A and B and C, this is okay. Okay, only one class among A, B, and C, check, and the class is specified first. Now, if you try to extend B and A and C, the first half of the constraints, the rules, is satisfied. You still have only one class among A, B, and C. However, because it's not specified first, it's not going to let you compile this. Okay? So let's use what we learned so far, and let's try to apply to a little example that features an interesting bug here. So we have a method here, count greater than. It returns an int. It's going to take two parameters, an array and an element. So it's supposed to tell us how many times the element parameter occurs inside the array parameter. So it's a good candidate for a generic method because the logic for this code can be written regardless of what data type are the element of the array. Okay, it's always the same logic. So the logic is you start your count at 0, and then you iterate over your array. So for each element E of your array, you test if E is greater than LM, then you increment your count, and when you're done iterating over the entire array, you return count. All right, so nothing fancy there. Now, the way we make this generic, obviously, is by saying that this generic method is going to accept a type parameter T. This type parameter T is going to be used to qualify the element. So we are going to have an element of type T, and the array. We are going to have an array of elements of type T as well. Okay, so this is how we turn this method into a generic method. And the logic is sound again. However, there is a little bit of an implementation detail here. There is a little problem. The problem appears right here. When you test if E greater than LM, you are going to get a compilation error. And the reason behind that is that the greater than operator is meant to operate on data types, not references to object. So there is still a way to fix that, okay? It's not the logic of our method that is wrong, it's more the way that we went about implementing it. So how can we possibly fix this problem? Well, there is a way to compare objects, right? But to do so, we need the classes of those objects to extend the comparable of T interface that is available in the Java collection framework. So let's try again, but using this, this hint. So in a nutshell, the comparable of T interface could look something like that. This is a simplified view, okay? But all that matters is you say, okay, I'm going to implement this interface comparable of T. So that means I'm going to provide a method compare to that returns an int, and the rule for the value being returned is you return 0 when the two objects are the same, negative when the first object, the one you are called on, comes before the one that you pass as parameter, and a positive value otherwise. Okay, and you take as parameter another reference to another object of class T. Okay, so that's, we have seen that already in the past. I mean, this is something that is really ubiquitous in the Java collection framework. So now let's see how we are going to extend, we're going to, use this comparable interface to rewrite our generic method. So count greater than is still the same, mostly, with the exception of those two yellow highlighted parts. So the type parameter here is not T simply any longer. It's T extends comparable of T. So we use that bounded type parameter notation that we learned about. And you can see that, as we mentioned when we started using multiple type parameters, you can actually extend something that is another type parameter, another parameterized type, sorry. No problem there. You can extend a double, an integer, a number, but also things like comparable of T, okay? And then once we say that our data type T, okay, is going to be something that extends comparable of T, then in the code we are allowed to use any method that is defined in the bound that we specified. So the bound that we specified is a class comparable of T, or interface in this case. Well, any method that is available in that class or interface is available for us to use in the code because of that bounded type parameter. So now we know that E is of data type T, which allows us to call compare to LM and test whether it's greater than 0. So we replace that greater than test, with a proper comparison between objects, but we make sure that anytime this generic method is called, the actual type parameter that is passed as type argument is going to be a T that extends comparable. If not, the compiler will warn us. Tiny little remark here. We use the keyword extend, okay? So don't get confused about, well, this is an interface, so maybe I should use implements here. No. Again, this is the context of the word extends being used here inside our definition of type parameter is to mean subclassing. So we are saying that the data type T, no matter what it is, subclasses comparable of T. Okay, and we use that like you saw in our example, whether this here on the right-hand side, comparable of T, is an interface or is a class or anything. We just look at types, okay? Not the specifics of whether they are interface, class, enums, or whatnot. And a last thing to take into consideration in this slide, well, actually, I already covered that. I mean, this is really, you need to look at this differently than when you look at the keyword extends, as part of the definition of a class, like class, employee, extend, person. That's totally different, okay? And that's it pretty much for our bounded type parameter, except that we have been covering so far the example that are, I would say, the most obvious, okay? The example that shows the nice side of bounded type parameter, how you can use them, what you can do with them. But if you pause now and you take a little bit of time thinking about this slide presentation here, this section of our lecture, you should have a lot of questions that come up, questions that try to reconciliate more specifically the bounded type parameter, which is a new technique we covered, with the old techniques of polymorphism. Okay, so think about that, try to see, if you could do what you can do with bounded type parameter with polymorphism. And then we are going to focus on that in our next video.